John D'Ambrosio. I'm a product and support engineer here at Advanced Motion Controls, and today we'll be tuning the current loop of an AxCent analog drive. The default current loop gain settings on AxCent drives are sufficient for most applications. Some systems, however, can benefit from alternative tunings. This video is intended to show how to tune an AxCent Analog Servo Drive. If you have a Digiflex or FlexPro digital drive, tuning can be accomplished through the software. Here are some reasons why you might need current loop tuning. Your motor or servo drive rapidly overheats at low current. You hear a vibration sound that comes from the drive or motor. The motor in use has a high inductance. The motor in use has a low inductance. Your system has a slow response time, or there is excessive noise problems. Here is what you'll need prior to tuning: the datasheet for your drive. App note number 15, current loop tuning procedure. You will need to be familiar with app note 15 as it explains in detail how to set up your system for current loop tuning, including the oscilloscope, function generator, and servo drive. Having the motor and drive system already configured, you should already be at the point where you can enable the drive and command current to the motor. Having the servo drive set to current mode with current limit safe for the motor. Please see the datasheet for switch settings. Finally, have all equipment readily available. This includes the oscilloscope, the function generator, the current probe, the servo drive, and the motor. This is the datasheet for the drive I will be using, the AB15A100. The switch settings are found on page 5. If you haven't already, please unplug the hall sensors and switch the phasing to 60 degrees. If you are not able to do this, please refer to app note 15 for more information. For this system, I will put the drive in current mode by switching SW1 to off and SW3 to on. Switch bank 3 will be used to set the proportional and integral gain. If your particular servo drive doesn't have tuning switches, please refer to app note 15 for more information. Some servo drive models have limited switch options for current loop tuning. Just select the best waveform from the available options. Some models have no switches at all, or you may not be satisfied with the results from the switch settings. If this is the case, contact technical support for more current loop tuning options. Hook up the positive wires from the oscilloscope and the function generator to the drive's reference input through the blue wires as shown. Then, connect the negative wires from the oscilloscope and the function generator to the drive signal ground through the green wires. We will then wrap the current probe around one of the motor leads that will be connected to the drive. Then connect the motor leads. Finally, we connect high voltage and ground to the drive. Now, let's begin setting up the scope. Your scope may look different, but the premise is the same. First, we will check the trigger settings. We want to reject high frequency noise and trigger on a rising edge. Then, adjust the waveform acquisition to show the average. When scaling the time per division, 2 milliseconds should be appropriate.
The channel with the reference in signal should be scaled to 500 millivolts vertically. The channel with the current probe should be scaled to 100 millivolts. These are only recommendations for viewing the waveforms. Feel free to adjust as necessary. The signal generator will serve as the command source to the drive. We want to provide the drive with a 100 Hz square wave at an amplitude of 1 volt. This will cause the motor to vibrate, but stay in one position. As you can see, this is what our current response looks like prior to tuning. There is a large overshoot which then levels off. Our drives are shipped with a high default current loop integrator value, so we will focus on decreasing this gain. Before we change the switch settings, we must turn the power off. This is for safety precautions. We just turned switch 7 on. Now we see that the overshoot has been reduced, but not removed. We are aiming for a smooth, overdamped step response. Let's turn switch 8 on now. We are getting closer, but still not quite there. Let's try turning switch 9 on. There we go. That response is much more appropriate. This will lead to a smoothly run application.